Learning objectives. In this chapter, the user would learn the following in detail: unit testing, integration testing, system testing, acceptance testing, white box testing, flow graph notation, cyclomatic complexity, graph matrices, control structure, loop testing, black box testing, equivalence partitioning, boundary value analysis, orthogonal array testing. User acceptance testing. An acceptance test can be understood as a way to check if a previously defined contract between the developer and the customer is still on track. Running those acceptance tests also ensures that no requirement change has happened in the meantime, and that everything is as it should be to satisfy the customer. Acceptance tests are useful because they capture user requirements in a directly verifiable way. They identify problems which unit or integration tests might have missed, and they provide an overview on how done the system is. How is a user acceptance testing (UAT) different from functional testing? User acceptance tests consist of a set of test steps which verify if specific requirements are working for the user. If the customer and the supplier agree on the product, the software development is done, legally and practically. Functional testing, on the other hand, and specifications of the software. It lacks the user component. A functional test could conclude that the software meets its specifications. However, it does not verify if it actually works for the user. The functional dimension is only one of many. Types of user acceptance testing: alpha and beta testing, contract acceptance testing, regulation acceptance testing, operational acceptance testing. Alpha and beta testing. Alpha testing takes place in the development environment and is usually done by internal staff long before the product is even released to external testers or customers. Alpha testing can also be done by potential user groups, but the important thing here is that it takes place in the development environment. The feedback collected from the alpha testers is then used to fix certain issues of bugs and improve the usability of the product. Beta testing, also known as field testing, takes place in the customer's environment and involves some extensive testing by a group of customers who use a system in their environment. These beta testers then provide feedback, which in turn leads to improvements of the product. Alpha and beta testing are done before the software is released to all customers. Contract acceptance testing. A developed software is tested against certain criteria and specifications which are predefined and agreed upon in a contract. The relevant criteria and specifications for acceptance must be defined when the contract itself is defined and agreed upon. Regulation acceptance testing, compliance acceptance testing. It examines whether the software complies with the regulations. This includes governmental and legal regulations. Operational acceptance testing, operational readiness testing, production acceptance testing. These test cases ensure there are workflows to allow the software to be used. This should include workflows for backup plans, user training, and various maintenance processes and security checks. Black box testing, behavioral testing, functional testing. It focuses on the functional requirements of the software, that is, sets of input conditions that will fully exercise all functional requirements for a program. Black box testing attempts to find errors in some categories that are incorrect or missing functions, interface errors, errors in data structures or external database access, behavior or performance errors, and initialization and termination errors. Black box testing tends to be applied during later stages of testing. Graph-based testing methods. It begins by creating a graph. Nodes represent objects, links represent the relationships between objects. Node weights that describe the properties of a node, that is, a specific data value or state behavior. Link weights that describe some characteristic of a link. Nodes are represented as circles connected by links. Directed link, represented by an arrow, indicates that a relationship moves in only one direction. Bidirectional link or symmetric link implies that the relationship applies in both directions. Parallel links are used when a number of different relationships are established between graph nodes. Equivalence partitioning divides the input domain of a program into classes of data from which test cases can be derived. Define a test case that uncovers classes of errors, thereby reducing the total number of test cases that must be developed. Test case design for equivalence partitioning is based on an evaluation of equivalence classes for an input condition. Using concepts introduced in the preceding section, if a set of objects can be linked by relationships that are symmetric, transitive, and reflexive. Equivalence class represents a set of valid or invalid states for input conditions. Input condition is either a specific numeric value, a range of values, a set of related values, or a Boolean condition. Equivalence classes may be defined according to the following guidelines. If an input condition specifies a range, one valid and two invalid equivalence classes are defined. If an input condition requires a specific value, one valid and two invalid equivalence classes are defined. If an input condition specifies a member of a set, one valid and one invalid equivalence classes are defined. If an input condition is Boolean, one valid and one invalid class are defined. GUI design and equivalence classes. Equivalence classes for programs that obtain input exclusively from a keyboard. One must account for the possibility of errors in data entry. For example, an application places a constraint on an input variable x. Assume integral values in the range 0 to 4. However, testing must account for the possibility that a user may inadvertently enter a value for x that is out of range. Suppose that all data entry to the application is via a GUI front-end. Suppose also that the GUI offers exactly 5 correct choices to the user for x. Impossible to test the application with a value of x that is out of range. Only the correct values of x will be input. It shows in the following figure. Boundary Value Analysis, BVA. A test selection technique that targets faults in applications at the boundaries of equivalence classes. While equivalence partitioning selects tests from within equivalence classes, boundary value analysis focuses on tests at and near the boundaries of equivalence classes. Certainly, tests derived using either of the two techniques may overlap. BVA procedure. Partition the input domain using unidimensional partitioning. This leads to as many partitions as there are input variables. Generate several subdomains in a single partition by using multidimensional partitioning. Identify the boundaries for each partition using special relationships among inputs. Select test data such that each boundary value occurs in at least one test input. Example to create equivalence classes based on BVA. Assuming that an item code in the range 99.999 and quantity in the range 1 to 100, equivalence classes for code E1 values less than 99, E2 values in the range, E3 values greater than 999. Equivalence classes for quantity E4 values less than 1, E5 values in the range, E6 values greater than 100. Example to identify boundaries based on BVA. Equivalence classes and boundaries for find price can be depicted as shown. Boundaries are indicated with an X. Points near the boundary are marked with a star. Example to construct test set based on BVA. Test selection based on the boundary value analysis technique. It requires that test must include for each variable values at and around the boundary. T1, code 98, quantity 0, and so on as shown. Comparison testing, back-to-back testing. It presents the same test to different versions of the system and compare outputs. Differing outputs imply potential problems. reduces the cost of examining test results, automatic comparison of outputs by comparator, possible when a prototype is available with regression testing of a new system version, difference report, orthogonal array testing, OAT. It provides maximum coverage with a minimum number of test cases by reducing the number of combinations, used to verify the large number of test combinations. OAT is used for finding errors associated with a faulty logic within a software component. L9 orthogonal array of test cases are created in orthogonal array testing. The L9 orthogonal array has balancing property, that is, test cases are dispersed uniformly throughout the test domain, represented by black dots in the figure. Result of tests using L9 orthogonal array in the following manner. Detect and isolate all single-mode faults. A single-mode fault is a consistent problem with single parameter. Detect all double-mode faults, consistent problem when specific levels of two parameters occur together. It is an indication of pairwise incompatibility or harmful interactions between two test parameters. Multi-mode faults. Orthogonal arrays can assure the detection of only single and double mode faults. However, many multi-mode faults are also detected by these tests. Integration testing. A systematic technique for constructing the software architecture. Conducting tests to uncover errors associated with interfacing. Objective: to take unit-tested components and build a program structure that has been dictated by design. Drawbacks of non-incremental integration. Construct the program using a Big Bang approach. All components are combined in advance. The entire program is tested as a whole. A set of errors encountered, but the correction is difficult because isolation of causes is complicated by the vast expanse of the entire program. Incremental integration. Direct opposite to Big Bang approach, the program is constructed and tested in small increments where errors are easier to isolate and correct. Interfaces are more likely to be tested completely, and a systematic test approach may be applied. Top-down integration testing, an incremental approach to construct the software architecture. Modules are integrated by moving downward through the control hierarchy, beginning with the main control module, main program. Subordinate modules are incorporated into the structure in either a depth-first or breadth-first manner. The interconnection of the main program and some subprograms is called the top-down approach. Programmers use temporary programs called stubs instead of subprograms which are under construction. The other name for stubs is called programs. A stub returns the control to the main program. In this approach, first parent modules are developed. After that, child modules are developed. Then interconnect parent and child modules. In the interconnection process, if there is any submodule under construction, then the developers create temporary program instead of submodules that is called stub. Depth-first integration integrates all components on a major control path of the program structure. Selection of major paths is somewhat arbitrary and depends on application-specific characteristics. For example, selecting the left-hand path components from M1, M2, and M5 would be integrated first. Next, M8 or M6 would be integrated. Then the central and right-hand control paths are built. Breadth-first integration incorporates all components directly subordinate at each level, moving across the structure horizontally. From the figure 3.2, components M2, M3, and M4 would be integrated first. The next control level M5, M6, and so on follow. There are 5 steps in top-down integration testing process. Step 1. The main control module is used as a test driver and stubs are substituted for all components directly subordinate to the main control module. Step 2. Depending on the integration approach selected, depth or breadth first, subordinate stubs are replaced one at a time with actual components. Tests are conducted as each component is integrated. On completion of each set of tests, another stub is replaced with a real component. Step 5. Regression Top-down integration strategy verifies major control or decision points early in the test process. What problems may be encountered when top-down integration is chosen? Most common of these problems occurs when processing at low levels in the hierarchy is required to adequately test upper levels. Stubs replace low-level modules at the beginning of top-down testing. Therefore, no significant data can flow upward in the program structure. The tester is left with three choices: delay many tests until stubs are replaced with actual modules, develop stubs that perform limited functions that simulate the actual module, integrate the software from the bottom of the hierarchy upward. This approach is called bottom-up testing. Bottom-up testing. It begins construction and testing with atomic modules, that is, components at the lowest level in the program structure. Because components are integrated from the bottom, processing required for component subordinate to given level is always available, and the need for stub is eliminated. A bottom-up integration strategy may be implemented with the following steps. Low-level components are combined into clusters, sometimes called builds, that perform as specific software sub-function. A driver, a control program for testing, is written to coordinate test case input and output. The cluster is tested. Drivers are removed and clusters are combined, moving upward in the program structure. Regression testing. Each time a new model is added as part of integration testing, the software changes. New data flow paths are established, new I/O may occur, and new control logic is invoked. These changes may cause problems with functions that previously worked flawlessly. In the context of an integration test strategy, regression testing is the re-execution of some subset of tests that have already been conducted to ensure that changes have not propagated unintended side effects. Regression testing is the activity that helps to ensure that changes do not introduce unintended behavior or additional errors. Regression testing may be conducted manually by re-executing a subset of all test cases or using automated capture playback tools. Capture playback tools enable the software engineer to capture test cases and results for subsequent playback and comparison. The regression test suite, subset of tests to be executed, contains three different classes of test cases. A representative sample of tests that will exercise all software functions, additional tests that focus on software functions that are likely to be affected by the change, tests that focus on the software components that have been changed. As integration testing proceeds, the number of regression tests can grow quite large. Therefore, the regression test suite should be designed to include only those tests that address one or more classes of errors in each of the major program functions. Smoke testing. It is an integration testing approach that is commonly used when software products are being developed. It is designed as a pacing mechanism for time-critical projects, allowing the software team to assess its project on a frequent basis. Smoke testing activities. Software components that have been translated into code are integrated into a build. A build includes all data files, libraries, reusable modules, and engineered components that are required to implement one or more product functions. A series of tests is designed to expose errors that will keep the build from properly performing its function. The build is integrated with other builds and the entire product is smoke tested daily. The integration approach may be top-down or bottom-up. Benefits of smoke testing. When it is applied on complex time-critical software projects, integration risk is minimized, quality of the end product is improved, error diagnosis and correction are simplified, progress is easier to assess. Testing strategies for conventional software. Unit testing, integration testing. Unit testing. Verification on the smallest unit of software design, that is, the software component or module. Using the component-level design description as a guide, important control paths are tested to uncover errors within the boundary of the module. Unit test focuses on the internal processing logic and data structures within the boundaries of a component. This type of testing can be conducted in parallel for multiple components. The module interface is tested to ensure that the information properly flows into and out of the program unit under test. Local data structures are examined to ensure that data stored temporarily maintains its integrity during all steps in an algorithm's execution. All independent paths, basis paths, through this control structure are exercised to ensure that all statements in a module have been executed at least once. Boundary conditions are tested to ensure that the module operates properly at boundaries established to limit or restrict processing. And finally, all error handling paths are tested. Tests of data flows across a module interface are required before any other test is initiated. If data do not enter and exit properly, all other tests are doubtful. Test cases should be designed to uncover errors due to erroneous computations, incorrect comparisons, or improper control flow. More common errors in computations are incorrect arithmetic precedence, mixed mode operations, incorrect initialization, precision inaccuracy, and incorrect symbolic representation of an expression. Test cases should uncover errors such as comparison of different data types, incorrect logical operators or precedents, expectation of equality when precision error makes equality unlikely, incorrect comparison of variables, improper or non-existent loop termination, failure to exit when divergent iteration is encountered, and improperly modified loop variables. Boundary testing is one of the most important unit testing tasks. Software often fails at its boundaries. Test cases that exercise data structure, control flow, and data values to uncover errors. Good design dictates that error conditions be anticipated and error handling paths set up to reroute or cleanly terminate processing when an error does occur. Unit test procedures. Unit tests considered as an adjunct to the coding step. The design of unit tests can be performed before coding begins, a preferred agile approach, or after source code has been generated. A review of design information provides guidance for establishing test cases to uncover errors. Each test case should be coupled with a set of expected results. Driver and/or stub software must be developed for each unit test. In most applications, a driver is the main program that accepts test case data, passes such data to the component to be tested, and prints relevant results. Stubs serve to replace modules that are subordinate to, called by the component to be tested. A stub or dummy subprogram uses the subordinate module's interface, may do minimal data manipulation, provides verification of entry and returns control to the module undergoing testing. Unit testing is simplified when a component with high cohesion is designed. When only one function is addressed by a component, the number of test cases is reduced and errors can be more easily predicted and uncovered. White box testing, glass box testing. A test case design method that uses the control structures to derive test cases. Flow graph, program graph notation. It depicts the logical control flow using the notation as shown. Each circle in the flow graph, called the flow graph node, represents one or more procedural statements. Arrows on the flow graph, called edges or links, represent flow of control and are analogous to flow chart arrows. Areas bounded by edges and nodes are called regions. When counting regions, each node that contains a condition is called a predicate node. Cyclomatic complexity. Cyclomatic complexity is a software metric that provides a quantitative measure of the logical complexity of a program. When used in the context of basis path testing method, the value computed for cyclomatic complexity defines a number of independent paths in the basis set of a program. Cyclomatic complexity provides an extremely useful software metric. Complexity is computed in one of three ways. The number of regions of the flow graph correspond to the cyclomatic complexity. Cyclomatic complexity, V of G, for a flow graph G is defined as V of G equals E minus N plus 2, where E stands for edges and N for nodes. Cyclomatic complexity V of G for flow graph G is also defined as V of G equals P plus 1, where P is the number of predicate nodes in G. The cyclomatic complexity of the flow graph it shows in the following figure. The flow graph has 4 regions. V of G, 11 edges minus 9 nodes plus 2 equals 4. V of G, 3 predicate nodes plus 1 equals 4. Graph matrices. To develop a software tool that assists in basis path testing, a data structure called a graph matrix. A graph matrix, connection matrix, a square matrix whose size is equal to the number of nodes on the flow graph. Each row and column corresponds to an identified node and matrix entries correspond to connections, an edge between nodes. Each node on the flow graph is identified by numbers, while each edge is identified by letters. A letter entry is made in the matrix to correspond to a connection between 2 nodes. For example, node 3 is connected to node 4 by edge B. Control structure testing. Broaden testing coverage and improve quality of white box testing. Condition testing. A test case design method that exercises the logical conditions contained in a program module. A simple condition is a Boolean variable or a relational expression possibly preceded with not operator. Relational expression format. E1, relational operator, E2. E1, E2 are arithmetic expressions. Relational operator is one of the following: less than equal to, not equal to, greater or equal to. A compound condition is composed of 2 or more simple conditions, Boolean operators, and parentheses. Boolean operators allowed in a compound condition include or, and not. A condition without relational expressions is referred to as a Boolean expression. Data flow testing. Example: the data flow testing method selects test paths of a program according to the locations of definitions and uses of variables in the program. Each statement in a program is assigned a unique statement number. Each function does not modify its parameters or global variables. For a statement with S as its statement number, def S equals X such that statement S contains a definition of X. Use S equals X such that statement S contains a use of X. If statement S is an if or loop statement, its def set is empty, and its use set is based on the condition of statement S. Definition use du chain of variable X is of the form X, S, S dash, where S and S dash are statement numbers. X is in def S and use S dash, and definition of X in statement S is live at statement S dash. Data flow testing strategies are useful for selecting test paths of a program containing nested if and loop statements. Loop testing. Loop testing is a white box testing technique that focuses exclusively on the validity of loop constructs. 4 different classes of loops can be defined, that are simple loops, concatenated loops, nested loops, and unstructured loops. Simple loops. A set of tests can be applied to simple loops, that are where n is the maximum number of allowable passes through the loop. Skip the loop entirely. Only 1 pass through the loop. 2 passes through the loop. M passes through the loop, where m is less than n. N minus 1, n plus 1 passes through the loop. Nested loops. Number of possible tests would grow geometrically as the level of nesting increases. This would result in an impractical number of tests. It suggests an approach that will help to reduce the number of tests. Start at the innermost loop. Set all other loops to minimum values. Conduct simple loop tests for the innermost loop while holding the outer loops at their minimum iteration parameter. Loop counter values. Add other tests for out-of-range or excluded values. Work outward, conducting tests for the next loop but keeping all other outer loops at minimum values and other nested loops to typical values. Continue until all loops have been concatenated loops. It can be tested using the approach defined for simple loops if each of the loops is independent of the other. However, if two loops are concatenated and the loop counter for loop 1 is used as the initial value for loop 2, then the loops are not independent. When the loops are not independent, the approach applied to nested loops is recommended. Unstructured loops. Whenever possible, this class of loops should be redesigned to reflect the use of structured programming constructs. Conclusion. In this chapter, we have covered the following in detail: unit testing, integration testing, system testing, acceptance testing, white box testing, flow graph notation, cyclomatic complexity, graph matrices, control structure, loop testing, black box testing, equivalence partitioning, boundary value analysis, orthogonal array testing.